a different data structure we haven't seen yet. So we're still talking about generics, though. Hopefully this works. Hang on, PowerPoint's acting up a bit. Just a second here. Okay. All right, so we've seen a list, and we've seen a stack. Now we're going to look at another data structure called a queue. So that's an example of a queue, right? So that's a queue. It's basically, this is just a line of people, right? So there's in a queue, there's the notion of a front and back of the queue, right? So the person at the front of the line, well, that's the front of the queue, right? When you get in line, assuming everybody's polite, right, you get in at the back of the queue. Right? If you're at a nightclub and you're a VIP, you might get in at the front of the queue, but that's a different story. That's actually something called a priority queue, and you'll learn about those in CISC124. But for here, we're only interested in the front and the back of the queue. Right? Now, like a stack, queues only have two operations. Right? So you can enqueue, right, where you add something to the back of the queue, and you can dequeue, where you remove something from the front of the queue. Right? And of course, it's always an error to try to remove something from an empty queue. To make a useful queue, it's often, it's nice to have other operations. Right? So it's nice to know how many elements are in the queue, so size. Right? It's nice to know if the queue is empty. Sometimes it's useful to look at the first element in the queue but not remove it. So that operation is called peek. And then occasionally it's also useful to know is something in particular in the queue. Right? So that's contains. Right? Search the queue for a particular element. Okay, so this is what enqueuing and dequeuing looks like, right? So in an empty queue, I've got these funny pointers F and B, right, for front and back. So in an empty queue, there's no front or back of the queue. Right? When you enqueue, an element appears at the front of the queue, and at the back of the queue, which is also the front in this case. Right? If I enqueue another element, right, it appears at the back of the queue, and now you adjust this arrow B to point at the new back of the queue. Right? And queue again, right? So the element appears at the end, adjust B, and so on, and so on. Right? Now when you dequeue, elements fall off the front of the queue, right? So they come out starting at F. Right? So when I dequeue an element, we get back the A, and then the element disappears. Right? Now this picture is deceiving. I drew it wrong. Mostly because I was lazy. I just copied the other PowerPoint slides. Right? So when you dequeue, the element comes off the front. Right? What this should really be showing is that everybody moves forward. Oh, there we go. Everybody moves forward one position. Perfect. That's what I wanted. Right? If you dequeue again, right, the B is going to come out. Oh, sorry. I see what's happening. It's animated. OK. So when you dequeue again, the B comes out, and then everybody moves forward one position in the queue. Right? If you dequeue again, the C will come out. Right? And everybody else moves forward one position in the queue, and so on. I'm just going to skip ahead now, right? And then so on. Right? And then you have the empty queue again. OK, so a queue is what's called a first in, first out data structure. Right? So the first person in line is the first person that gets out of line. Right? So first in, first out. Or you can also call it last in, last out. So it's also called a LILO data structure. Right? That's opposed to a stack, which is first in, last out, or last in, first out. Right? And like a stack, so even though this data structure seems ridiculously simple, right? I can only do things at the front and back of the queue. Turns out they're really useful, right, in computer science and engineering. Right? So basically any big website that you visit where you're shopping for something, there's a bunch of queues. Right? So when you put something in your shopping cart, typically what happens is the thing that you bought gets taken out of inventory and stuck into a queue somewhere. Right? Web servers use queues to service requests. Right? So if you are visiting a website, right, there could be lots of people visiting the website at the same time. Right? The web server can only do one thing at a time. So everybody who visits the site, you just get put into a queue, and then the visitors get served in order. Right? That's a simple. Both of these are simple example, are overly simplistic examples. Right? In real life, it's a lot more complicated, but you get the idea, I think. Right? Your operating system has a bunch of queues. So your operating system is basically responsible for the resources of your computer. Right? So it manages what gets access to the CPU, what gets access to the disk, what gets access to the network, and so on and so forth. Right? Often it's the case where you have many programs running on your computer at the same time. They all need access to, say, the CPU. Right? They can't all have access to the CPU at the same time, so they all get put into a queue. Right? And then they get served in order. There's a classic algorithm in computer science called breadth first search. Right? The easiest way to implement breadth first search is using a queue. And then there's actually a whole branch of mathematics devoted to what's called queuing theory, believe it or not, which you can probably study if you wander over to the math department and ask for a queuing theory course. Sometimes it's taught in computing science. Okay, so if I want to make a queue, then like a stack, it turns out there's lots of ways you can implement a queue. Right? We can use a list, we can use an array, we can use a bunch of nodes. Right? And so it's going to be very similar. The story is going to be similar to the stack story. Right? We're going to make an interface. We know how to make generics, so we might as well make it generic now. Right? And then we're going to implement the queue in a bunch of different ways. So we make our interface called queue. Right? A queue holds some elements, so we have our generic type here, E. Right? And then we have our methods. Right? So there's size is empty, NQ, so add that element to the back of the queue. Right? DQ, take the element out from the front of the queue. Right? And then we're going to do front and back. So return the front element of the queue without taking it out, and return the back element of the queue without taking it out of the queue. Right? Again, we have a default method here. Right? So remember, you can have interfaces are allowed to implement methods. Such methods are called default methods. Any class that implements the interface gets the implementation of the default method. Right? When you implement a default method, the only thing you can do inside the method is use methods that are in the interface. Right? So here I'm using this size. Right? That's fine because the interface says there's a size method. Right? That returns an int, so I'm allowed to write this size equals 0 and return that value. Right? If you want to, so if a class that implements the queue interface is allowed to change how this method behaves. Right? So you can still override a default method. Right? But every class actually gets an implementation of the default method. All right, so if you go back and look at the picture of a queue, then if you implement a queue using a list, right, when you NQ, we just add to the end of the list. So that's exactly the same as with the stack. Now, when you DQ, though, you remove the front element of the list. Right? So it's dead easy to implement, right? Fits on almost one slide. Right? So if I want to implement a queue using a list, we implement the queue interface. Right? We pick a name for our class, so I'm just going to call it list queue. Right? Internally, there's a field that's a list, right, of the element type E. Right? So our constructor has to make a new list, right? Because that's what a constructor does, right? It initializes all the fields of the class. Right? So we make a new array list and assign that to queue. Right? Size is easy, right? Because all of our elements are in a list, so I can just ask the list for its size. NQ, we just add to the end of a list. That's easy too. We just call add. Right? DQ, private throw if empty. Okay, so I've got a little private method here that throws an exception if the queue is empty. Right? So that's easy to implement too. Just call isEmpty. If is empty returns true, throw an exception. Right? And now we have DQ. Now DQ removes the first element from a list. I don't know why there's two. These are duplicated, I'm sure. Right? So first check, is the queue empty? If it is, throw an exception. Right? And then call remove, right? Passing in index 0 to remove the first element of the list. Now, the problem with removing something from an array-based list, which we saw, well, not the problem. So we saw that when you implement an array-based list, if you remove something from the middle of the list, right, then you have to move all of the following elements forward one position in the array. Right? So because we're using an array-based list here, right, the same thing is going to happen. When I remove the first element out of the list, the remaining elements all have to be moved forward one position in the list. Right? And that takes time proportional to the number of elements in the list. So our DQ method has complexity big O n, right? Which is not necessarily a good thing. Okay, front is easy and back is easy if you have the method throw if empty, right? So if the queue is empty, there is no front element, so we throw an exception. Otherwise, return the element at index 0 of the list, right? Back returns the last element of the list, but that's easy too, right? Throw if empty, and then ask the list for the element at the end of the list, right? So it's always the size minus 1. ToString's easy too. I just asked the list for its string representation, and now I've got a ToString method for free as well. If you wanted equals, you could just call the list version of equals, and that would work too. Right? Okay. Any questions about the list implementation? Right? Notice that all the methods are basically 1 or 2 lines, so it's actually really easy to do. Okay, so keep in mind push. Oh, not push, sorry. Let's see. So DQ, right, we know is always in big O n, right, because you have to move all the remaining elements forward 1 position. NQ, right, so an array-based list, array list is an array-based list, right? So if the array is full, that's in the list, then when you add a new element to the list, it has to expand the size of the array and copy all the old elements into the new array, right? So NQ is also, worst case is also big O n, right? It turns out on average this is big O1, but that's a topic for your algorithms course, right, where you talk about more about complexity. So it turns out on average it's big O1, but worst case is big O n. So you have a queue implementation where the 2 main methods are both have complexity big O n. All right, so we're just going to repeat what we did with list and stack, right? So we've done it with a list. We've implemented queue with a list, so now let's do it with our own array, right? Now, when you do it with an array, things get a little tricky, right? Because remember in a list, when you add to the list, we always add at the end, right? So the array grows from the end of the array, right? With a queue, it's a little bit tricky because we're going to remove from the front, right? And we actually want to try to avoid moving all the elements forward in the array if we can, right? Because if we can avoid that, then we have complexity big O1 for DQ, right? And it turns out there is a way to do it. It's a little bit tricky, right? So remember in our array-based list, we had 2 fields, right? We had an array, right? And we had the size of the array. Sorry, we had 3, right? No, we had 2. We had the array, and then we had the last element of the array. Have we done list yet? We did stack, right? So in a stack, we had the array, and then we had the top element of the stack, right? The index of the top element. Right here, we're going to keep track of the array. We have the size, front and back. So front is going to be the index of the element that's currently at the front. Right? Back is going to be the index of the element currently at the back. All right? So we're going to keep track of 4 things in this implementation. So here's your brand new empty queue with an array, right? So the front element is the element that's currently at the, that's what I'm saying? Front is the array, but currently at the front of the queue. Did I do that right? Hang on, sorry, just give me 1 second here. I just want to check the implementation to make sure I actually did this right. Front is 0, okay. Array index of the element currently at the front. All right, so I guess it looks like, so in an empty queue, I'm going to start out with the front pointing at 0. I think this is actually supposed to be, just a second here, let me quickly check something. No, I am doing it that way. All right, I guess there should be an extra line here. Array index of the element currently at the front of the queue or 0, it's not necessarily 0 all the time. Or I guess if the queue is empty, it's going to be the index where you're going to put the front element of the queue. You'll see why in a few moments. Right, so in an empty queue, we're going to start with front equal to 0 and back equal to -1. All right, so n-queuing an element works exactly the same as pushing an element onto the stack. Right? We're going to add at the end of the array, at the end of the queue. Right? All right, so if the length of the array array length, sorry, if array length, what is that? If array square bracket length. What the heck is that? If array equals size. That's not right, sorry. If array equals size, make a new array. What on earth is that? That's not right at all. If array length? Why is it the array length? No. Array, sorry. Oh, hang on. That should be if array dot length. Okay, so if the size of your queue is equal to the length of the array, then you know that the array is full, right? So the queue is full, well, the array is full, so I have to make a new array, right? Then I have to copy all the elements into the new array. Now remember, back is the index of the element that's currently at the back, right? So if I want to add to the, if I want to add a new element to the queue, then I move back one position to the right, right? So we go one position to the right, and then I set the element at array index back to the n queued element, right? And then you add one to the size of the queue. Right? So after one in queue, right? So I'm going to move back one position to the right. Right, so back's over here, so I'm going to move it to 0. Right? I'm going to set that element to the n queued element, and then I'm going to add 1 to the size of the queue. Right? So we now have a queue of size 1. Notice that front and back now point at the, are both pointing at the same element. Okay, after a second enqueue, right? So to enqueue another element, I'm going to move back one position to the right, so it points at the 1. I'm going to set that element to the n queued element, and then I'm going to add 1 to the size. Right, so that's now 2. One more time, right? So enqueue another value, so I'm going to move back one element to the right, set the element in the array, and then add 1 to the size, so it's now 3. Right? And if you do it a few more times, you end up with the following queue. Right? So we've got a queue of size 5, right, with the elements A through E. Okay, so what about dequeuing an element? So if I want to dequeue that element, right, so I know front is pointing at that element, right? So I have to remember that there's an A there, because I need to return the A. Then I'm going to move front to the right. Sorry. I need to remember there's an A there. I'm then going to delete the A from the array by writing null into the array. Then I'm going to move front to the right. So this is different. We haven't done this before, right? So I'm going to remember what's at the front of the queue. I'm going to remove the element at the front of the queue by setting the element to null, right? You know, you see why we have to set it to null in a few moments, right? We didn't do this with the stack. With the queue, we have to do it this way, right? Front now moves one position to the right, right? So remember the A, remove the A with null, move front to one position to the right, right? And then return the element that we remembered. Right? So this is, right? So we dequeue one element, right? So remember that there's an A there, set that element to null, move front 1 to the right. Decrease the size of the queue by 1 because we removed an element. Right? Dequeue again, right? So remember that there's a B here. Erase the B by setting it to null, and then shift front 1 position to the right. Right? And so on, right? So if I remove 2 more elements or dequeue 2 more elements, right? Front now points at the E, right? And we have a queue of size 1. Right? Notice that any unused positions in the array are always set to null. Okay, what happens if I dequeue again? Right? So we just apply the dequeue algorithm, right? So remember that there's an E here, right? Null out the element, so set it to null, and then move front 1 position to the right, right? And you end up with this picture here, right? And so we end up back in the situation where back is 1 position to the left of front, right? And the queue is empty, right? So that looks like the empty queue, but remember at the empty queue, back was up here and front was over here. Right? Now, you might wonder, why are we doing all of this, right? So by implementing dequeue this way, right, all I'm doing is shifting this index front, right? I'm not moving all the elements forward in the queue, right, which you would have to do in a list, So in a queue, right, if I'm implementing it myself with my own array, right, DQ is always O1. Right? All I do is remember this element, right, set it to null, move front by 1, and then return the element. Right? So that's just a constant number of operations. Right? So by implementing a queue with our own array instead of using a list, right, we now have a queue that can DQ in O1 time, right, which is much better than ON. Right? Okay, if we NQ again, well, then everything just repeats itself, right? We move back forward to the right by 1, right? Add the element at that index, and then increase the size of the queue by 1. Right? So there's our queue of size 1. Now back and front both point at the same element. Okay, if I NQ a bunch more elements, right, back now ends up at the end of the array. But notice that the queue is not full, right? There's space for 5 more elements. Right? So at this point here, right, what I don't want to do is I don't want to expand the size of this array. Right? So in a stack, when you hit the back element of the array, the last element of the array, we now expand the size of the array. Right? But I'm not going to do that here because I've still got room in the array. Right? It's just that now they're at the front of the array. Right? So if I NQ again, I'm going to move back 1 position to the right. Right? But now it falls off the end of the queue. Right? So what do? We just wrap it around to the front. Right? So when I add 1 to back, right, I'm going to get 16. 16 is the size of the array. Right? So if I add 1 to back, compute the remainder after dividing by the size of the array, that will give me the index of where I wrap to. Right? So back wraps around to the front of the array. Right? And notice that back can be less than front in a non-empty queue. Right? So it's not always the case that in an empty queue, back is, what did I say there? Back is 1 less than front in a full, back can be less than front in a non-empty queue. Right, so normally in a non-empty queue, right, back was always over here somewhere, right? So back was always greater than front. But that's not the case, right? Back can be to the left of front in a non-empty queue. Okay, so what happens when the queue is full, right? So when the queue is full, back is, in this case, it's to the left of front, right? It's 1 position to the left of front, right? Now remember, if you remember a few slides back, in an empty queue, back was also 1 element to the left of front. Right? So you can't use the condition is back 1 element to the left of front to check if it's an empty queue, right? Because it could be full as well in this case. Okay, so now our queue is full, right? So now if I want to NQ another element, this is the point where I have to expand the size of the array. Okay. Oh, I guess I'm going to DQ first. So I'm going to show you that the same thing can happen to front, right? So notice that back wrapped around. Well, front can also wrap around. Right? So if I DQ all the elements, so I get to the P, right? The front now points at the last element of the array. If I DQ again, right, you just apply the DQ algorithm, right? So remember that there's a P here. Null out the P, move front 1 position to the right. But when we do this, it falls off and comes back to the front, right? And you end up with that, right? So front must also wrap to the front of the array. Now, if I take this array and draw it as a circle instead, right, and then you end up with the following picture here, right? So I guess Q, so that's index 0 of my array, right? Whenever I NQ something, right, back moves clockwise, right? So if I NQ a new element, the UV, I guess, right, I'm going to add it here, right, and then back moves clockwise. Whenever I DQ an element, right, front moves clockwise, right? So we remove the Q, move front clockwise, right? And so Q, when you implement it in the way that I showed you, it's often called implementing Q as a circular array, right? You just imagine that the array is just a big circle, and you just keep on going around the circle. Right? Okay, so how do we implement this thing? So we need an array to hold our elements, right? So we're going to use an array of object, right? Because we can't use an array of type E, unfortunately, in Java, right? We have to use an array of type object, right? We're going to keep track of the front element, the index of the front element, the index of the back element, and the number of elements that are actually in the queue. Right? To make a new queue, a new empty queue, right? What do? Make a new array, right? Now, remember here, when I make this array, right, Java automatically sets all the elements of the array, right? If the type is a reference type, then it automatically sets all the elements of the array to null, right? So you don't have to do that yourself, right? You also have to remember that the array is full of null values, right? If this is a primitive type, then it fills it with zeros, or false if it's Boolean. We're going to set front to 0. We're going to set back to -1, and we're going to set the size to 0. Right? How do I copy another array queue? Right? So can I copy another array queue? Well, to copy another array queue, I just copy that array. I copy the front value, I copy the back value, and I copy size. Right? But that's easy. Right? Copy the array, you use arrays copy of. Right? To copy front, it's just an assignment. Same with back, and same with size. Right? So the copy constructor is no problem here either. All right, what about front? Right? Well, the front, so if I try to if I ask for the front element of an empty queue, that's an exception. Right? So here I'm going to use isEmpty. I guess I should have made another method, but it's fine. Right? Otherwise, I want to return the element, right, at the front index. Right? So that's easy. I just ask the array for the element at the front index. Right? Now remember, our array is an array of object. Right? But front needs to return an element of type E. Right? So what I have to do is I have to take that element and cast it to type E. Right? If you don't do the cast, the compiler will complain. It'll say you're returning an object instead of an element of type E. Right? So you have to do the cast. Back is the same, except instead of returning the element at the front, we return the element at this back. Right? So those are easy. DQ, can't DQ an empty queue, right? So we'll throw an exception if the queue is empty. Right? And now you just implement the 4 lines of the algorithm. Right? So remember what the element is at the front of the queue. Well, that's easy, right? You could also call front here. Right? You could also write elam equals this dot front. So call the front method. Right? That will also throw the exception for you. So you don't even need the check here. You can just call this dot front right here. Right? So that'll give you the element at the front of the queue. Null out the element at the front of the queue. Right? Now remember I told you I'm going to move front 1 position to the right. Right? But also remember that front can fall off the end of the queue. Right? And if it falls off the end, I need to make it wrap around to the front. So the easiest way to do this is to add 1 to the front of the queue. Right? And then divide by the length of the array and compute the remainder. Right? So if this dot front becomes, if this front plus 1 is 16 in this example, right? Then when I divide by the array length, which is also 16, right? I get 1 with a remainder of 0. Right? So this front becomes 0 and it wraps around for me nicely. Right? So the remainder operator in Java, also in Python. Python you have // instead. It turns out they're really useful when you need to implement these circular ranges. Right? Decrease the size of the queue by 1 and then return the element. Right? So it's just the 4 lines of the algorithm. Any questions there? The only slightly interesting thing is this line right here. Right. Question?
Sorry, so could you go back to the when back wraps around all the way?
This is for DQ, so this is going to be front wrapping around.
No, I'm asking about. Well, I mean, I guess in general.
Yep.
Let's say if you have back wrapped all the way around.
Yep.
Where it's just 1 position in front of front.
1 position behind? Oh, sorry, in front. Yes, okay. Yeah.
In front of
Yep.
front.
Yep.
What happens when you need to make that queue bigger?
Oh, we're going to get to that. That's a good question. We're going to get to that. In fact, we're going to do that right now. Okay. All right. So resizing the internal array when it reaches its capacity is slightly more complicated than for a stack. Right? So remember, for a stack, we fill up our array, right? And then we say, oh, the array is full. If I want to push another element on the stack, I need a new array. Right? So I make a bigger array, and I just copy the elements into the new array. Right? And now there's a space at the back of the array. With the queue, it's different. Right? Because with the queue, the back of the queue is not necessarily the back of the array. Right? So for example, here's my full queue. Right? The front element is the F and the back element is the U. Right? So the naive way of doing this, right, is to use arrays.copy and just copy this array into a bigger array. Right? Now if you do that, you end up with the following. Right? So I end up with a copy of this array sitting at the front of my new array. Right? And now all of the empty elements are at the end of the array. Right? But notice that back is over here, but the next empty element is over here. And that's a bit of a problem, right? Because now all my algorithms break. Right? Furthermore, if I dequeue a bunch of stuff, I end up at if I dequeue a bunch of stuff and get to the P, right? If I dequeue again and I just apply my dequeue algorithm, I end up at null, right? Because I'm not going to wrap around because there's more elements in the array, right? So now we end up at null, and that's also a problem, right? So we can't just use arrays copy of and hope everything's going to work. Right? So what you have to do, well, one way to solve the problem is, right, is when I copy the array, so when I copy this array here, right, I'm going to unwind the array so that the front is at the first element of the new array. Right? So that would be one way to do it. Right? So in other words, right, instead of just copying this into here, I'm going to copy front to there, then that one to there, and then the third element to there, and so on and so on and so forth. Right? And then that works fine. Right? So now I've got a queue where the front of the queue is the F, right, at the front of the array. Right? The back of the queue is somewhere in the middle of the array, but the next free element is the one immediately after back. Right? And that's exactly what I want. So this is one way to solve the problem. There are other ways to solve the problem. Right? Okay, so let's do it that way. Right? So let's ignore the if statement up here, okay? We'll just ignore that. So instead, we'll implement our basic NQ algorithm. Right? So the basic NQ algorithm says, right, move back one to the right. So that's this dot back plus 1. Now remember, back can fall off the end, so I have to wrap in the exact same way that I wrapped front. Right? So just divide by the length of the array, compute the remainder. Right? And that wraps the value correctly. Right? Set the element at this back to elem, right? And then increase the size of the queue by 1. All right, now what happens if I have to do the expansion? Right? So if I have to do the expansion, first thing you do, make a new array, right? That's bigger than the current array, right? So I'm going to multiply, my new array is going to be 2 times the length of the old array, right? And now you have to do the copy yourself, right? So I want to copy, I want to copy starting at front, right, into the first element of the new array, right? Then front plus 1, new element of the array, and so on and so on. Right? So how do I do this? Temp I equals this array. Right. Okay, so how are we going to do this? So the destination index starts at 0. Right? So I want to copy index 5 to index 0. Right? Then index 6 to index 1. Right? So the destination index starts at 0. It goes up to the size of the original array minus 1. Right? So I'm going to start at 0, right? Go up to, but not including, the current size of the queue. Right? Go up by 1 each time. Right? So I is the index of the destination array. Right? Now what's the corresponding index in the source array? Right? So when I is 0, right, front is 5. Right? When I is 1, front is 6. Right? All the way up to here, right, where I have to fall off the end of the queue again, off the end of the array, sorry. So how do we do that? So the source index is front, right? Front plus the destination index, right? So in this case, plus I, right? Now remember that this is the index into the old array, right? So when I wrap around in the old array, I have to go back to 0. So again, divide and take the remainder after dividing by the array length, the original array length, right? It's a bit tricky here, right? This has to be this dot array length, not temp dot length, right? You have to remember that the source array is this dot array and not temp, right? So the destination array element is equal to the source array element, right? Making sure that you always wrap the source array index. Right? After you've done that, right, you've copied all the elements into the new array. So now the array belonging to the queue is equal to the new array. Front now changes, right, because the front of the new array, the new front index is 0, and the new back index is equal to the size of the queue minus 1. Right? Once you've copied all the elements over, you can then go ahead and add the new element to the queue. Right? Does that answer your question?
I think so.
Okay, so that's how you do it. That's one way to do it. Right? It's not the only way to do it. Right? The other way to do it is to, there's probably a bunch of ways to do it. Right? Another way you can do it is, so if this is your original array, so we'll just make an array of size 3. Right? If this is so this is front, obviously this is back, right? If I expanded this array to 6, 1, 2, 3, 1, 2, 3, right? The other way you could do this is just to, how would you do this? BC, yeah, you would do it this way. So you could do, you can make sure that this is always at the end, right? The front part of the queue goes to the end of the new queue, right? So that becomes BC and that becomes A. So that works too, right? And you can do whatever so that works fine. If you really wanted to do something weird, right, you could also do it this way. There's no reason to do it this way, but you can do it, right? All that matters is that you put the elements of the queue into the new into the new array correctly, right? So you could do it this way, ABC, like that, right? So any of these are possible and correct. This is weird. I don't know why you do it this way. This is also a little strange, right? This is probably the most quote-unquote obvious way to do things and have it work correctly. Right. But yeah, all that matters is that the elements, did I do that right? B, C, no, I didn't. Oh yeah, sorry. The back of the, oh, this is wrong, sorry. I should have written them in alphabetical order. That's dumb. A, B, C, so that's the back, so I have to put the A here. Sorry, like that. Right. So as long as you copy the elements into the new array so that they're in the correct order, everything will work out fine. Right. Of course, you have to adjust front and back accordingly. Okay, so what is the complexity of enqueue in this case? Right. So most of the time, so when I don't have to expand the array, right, enqueue is 01. Right. When I have to expand the size of the array, I have to do this copy. So now it becomes ON. Right? So DQ is now 01, which is better than for the list, right? Better than for the array list implementation, right? NQ still has the same complexity as the list implementation, right? It's still worst case ON. So again, so after you take your algorithms course, maybe after you take your algorithms course, right? You might be able to analyze this and show that on average it's 01. Right? I don't know if you will. I don't know if they'll do that for you or not. Okay, what time do we have here? Sorry, does anybody have the time? Okay. All right, so you had a similar question to this on the last assignment, right? So on the last assignment, you had an array stack, right? And I asked you to implement a copy constructor that copies another stack, right? You didn't know if it was an array stack or some other kind of stack. You just had to copy another stack, right? And so the trick there was to make another stack or list, pop the stack you want to copy into the new stack or list, right? And then push everything back onto the new stack and the old list and the old stack. Right? So for Q, it's similar, but the algorithm is slightly different, right? If you want to copy another Q, right, can be equal to, right, if you want to copy another Q, right, then you also need a second temporary data structure, right? For equals, where a Q instance can be equal to another, oh, sorry, this should be where an array Q instance can be equal to another array Q instance, right? So this is asking you to implement equals just for array Q, right? So how do you compute equals if one array Q is equal to another array Q, right? So what you can't do, right, what you have to remember in this question here is that you can have two Qs, and their arrays can look like the following. So A, B, C. I don't know why I wrote that in the wrong order. So there's front, there's back, right? That Q is equal to, or should be equal to, this Q, right? Because they both represent Qs where the first element is an A, the last element is a C, sorry, front, back, right? And the middle element is a B, right? So those two Qs are equal, it's just that their arrays are not equal, right? So the obvious way to implement this doesn't work, right? The obvious way to implement this is use arrays.equals, right? And check if the arrays are equal. But that doesn't work because these two Qs are equal, and their arrays are different, right? And so for this, implementing equals is a little trickier, right? You actually have to iterate over the elements of both Qs and compare them one at a time yourself, right? You can't rely on arrays equals to do it for you. Okay, I guess I'll stop. Yeah, I'll stop there. That's fine. What is the next lecture? Sorry, just let me quickly check what the next lecture is about. I think it's a list, right? Yeah, it's a list. Okay. So I think we finally get to a proper list. Yeah, that's what's going to happen. Okay. Any questions? Assignment comes out in probably an hour or two, or maybe a little bit more, but it's just about done. And that'll be the last assignment. So for this assignment 6, make sure you read the assignment document, because the assignment document tells you how to implement everything, right? It literally explains step by step how to do every method that I'm asking you for, right? It's a little bit, the reason I do that is because, one, you don't have that much time to do the assignment. And two, it is something that's a little bit new. We haven't done it yet in the course. We've got all the ideas, but I'm asking you to implement a map, right? Which is a little bit more complicated than implementing something like a list or a stack or a queue, right? But the assignment lays out everything step by step, right? It looks long, but make sure you actually read everything, okay? All right, I will see you next week, or I guess during office hours today.